Okay, why don't we get started? Welcome everyone, and I hope you're enjoying your warm summer so far. And got a couple of announcements to make. Not too much. Whoops! I realize my computer is playing back everything I'm saying 10 seconds after I say it, so that's a little disconcerting. Okay, I got that fixed. So, what's different about my announcements tonight is not that I'm just going to remind you that Chabot is closed and we're doing everything virtually, but that Chabot is starting to plan its reopening. And if you haven't heard, the Chabot Space and Science Center is planning on a November reopening, and that's going to be a full opening to the public for both the telescope decks as well as for the museum part of the Science Center. For those who are not aware, the Chabot Space and Science Center has become an official NASA visitor center. So there's going to be new exhibits, a lot of participation and input from NASA Ames. And so we anticipate a somewhat different experience for those of you who join us upon the reopening. And there'll be more about that in the future. The EAS may have the opportunity to reopen some of its activities a little bit earlier. We're talking with Chabot about possibly opening the Telescope Makers Workshop in September, and there'll be more on that if it actually happens. And there may be some member viewing nights for EAS members and Chabot members before the actual Science Center opening. But all of that is still in the discussion phase, so we don't have any definitive answers. We also haven't yet contacted schools and scouts and those types of institutions to find out what their plans are for astronomy outreach. So there will be more information about that as we start reaching out to the community and making contact with those institutions who have often used our outreach services to teach the kids about astronomy. So we'll see how that all goes. Anyway, that was it in the way of announcements. It's exciting. I feel like we're coming out of hibernation, and hopefully it stays that way. Let me see if I could dig up Dave Rodriguez here. Let's see if he's under. Oh, there he is. Dave? Dave? There you are.
Thank you for letting me out of that hole, Rich.
Yeah. I had to crawl under the table there to find you.
I think you were taking tonight's talk a little bit too literally.
Yeah.
So we have a very exciting talk tonight. When a friend of mine emailed me about it, some information about it, I was very excited about it for reasons that I'll talk about in a little bit. But I want to also mention that tonight's talk is actually related to next month's talk as well in a very broad sense, because next month we're having Dr. Mark Raymond, who is at JPL, and he is the chief engineer for the Dawn mission, which did an ion drive probe. I mean, this sounds almost like science fiction. Ion drive. I had kept they could teach us a thing or two. Ion probe drive, ion probe to both Vesta and Ceres. Rich and I and Rebecca saw this talk at RTMC, and it was a great talk. And it was funny, it was informative. And again, too, what's great about it also, it's related to tonight's talk, because tonight we have Dr. Arianna, I'm going to try to pronounce it correctly, Gleason-Holbrook. Again, I'm very excited about tonight's talk as well, because we so often hear these horror stories about asteroids wiping out life potentially. I remember one time I was being interviewed on KCBS, and I said, oh, by the way, if my asteroid were to hit the Earth, it'd be the equivalent of 8.5, I forget, it was 7.5 billion megatons, and I said it would be probably an extinction event. Arianna has an asteroid named after her too. By the way, hers is very close. Her number is very close to the number of our previous president, Carter Roberts, who is, I think, 10683. And Arianna, you're 106. I forget what. Are you on?
Oh, yes. Sorry, I'm here.
Okay.
Yeah, 39. Yeah.
10639. So it's a small solar system. So Arianna did her undergraduate work at one of my favorite institutions, and I know it's one of Rich's, University of Arizona at Tucson, not in Phoenix. She then did her graduate work at another one of our favorite institutions, UC Berkeley, where she got her PhD in geosciences, and has done some really neat work. And boy, I wish I could talk more about your bio, because that's just really interesting as well, Arianna. And now she's at the best institution in the world, Stanford University, where she works at SLAC, Stanford Linear Accelerator. And she does this really, really neat research, and all about shocking impacts. So tonight, shocking origin, meteor impacts, and the origin of life. And without any further ado, Arianna, I hand over the podium to you.
Just a reminder, we will be taking questions at the end of the presentation, and Dave and I will be curating those and doing it as a panel with Arianna at that point.
Great. Thank you so much. My audio and PowerPoint are clear. Thumbs up.
You're fine.
Good.
Wonderful. Thank you so much. It's a great pleasure to be here. My name is Arianna Gleason. I am a staff member at SLAC National Lab, an adjunct faculty at Stanford University Geosciences Department. And it's my great pleasure and honor to be with you this evening, giving this presentation. Tonight, I'm going to share with you some exciting ideas, exciting hypotheses on the origin of life and how we are actively pursuing experimental and theoretical work here in the Bay Area at some of our local facilities. The origin of life is a fantastic and sort of timeless question. Could be philosophical, could be religious, but here we're going to approach it from a scientific methodology and think about the different hypotheses for the origin of life. And look into one that in recent years has gained quite a bit of traction and interest, thinking about the opportunity, the recipe for life, developing in an impact in a collisional event scenario, where the energy that's deposited in nanoseconds is actually the key, holds the key to building up the complexity of life. And so we'll talk about that in a bit of detail. But if that is a pathway forward for understanding this exciting question, origin of life and the buildup of that complexity, how do we visualize that? How do we see that in real time in a laboratory setting, in the appropriate setting? Well, we need really fast and novel kinds of photography. So we're going to talk about how we're leveraging local facilities here and other experimental platforms actually across the globe to visualize the mechanisms that actually play a role in possibly the origin of life. And I think at the end you'll find, and probably the take-home message of the entire talk, is that life, or at least the precursor, the necessary components for life, are far more common than previously thought. So the search for life, are we alone? And the origin of life is really timeless. And here I show a photograph of a magazine cover, even from many years ago. And it's asking the question, what is the recipe for exobiology? What is the recipe for the components here? And essentially you need a location on which to cultivate and develop the molecular complexity. You need the appropriate chemicals to include in sort of harvesting that complexity. So you need the right chemistry. You certainly need water. That's a key piece that we've seen across the board. And then you need energy, an energy source to bring all of these different components together in the right form. And it's an emergent property that could form from these different components in that recipe. And the different forms of energy that are talked about, you could think stellar, the light from the sun, different sort of stellar energy input, tidal inputs, geothermal. We're going to also talk about that. And now we're putting forward in a new way, shining a new light on the opportunities of impact events. And in fact, it was remarked earlier, we think often of collisional events, massive collisions between planetary bodies as destructive, which they are, but it might also have this unique opportunity, provide this unique opportunity for kickstarting what's required for life. And in fact, it might be far more common than we think. So prospects for life in the universe, if we just zoom out a little bit and think about our context here, the universe has hundreds of billions of galaxies. And physics, Mother Nature, has had 14 billion years to figure out how to do this right. So that's a lot of opportunity and a lot of time. And if you think each galaxy has of order hundreds of billions of stars, and each of those stars could be considered a sun. Now, we found even more recently that most stars have planets, different bodies that orbit these suns. And it's really fantastic to think about that. In searching recently, in fact, you can look on some local sites, NASA keeps track quite well, these different exoplanets that have been discovered that orbit the sun, and some of them are in this most advantageous region, this habitable zone. And so over 4,000 exoplanets have been discovered and confirmed. And of those, as of a few months ago, last I checked, 60, probably over 60 now, have been then confirmed to be in this habitable zone. So they're in this perfect Goldilocks region that satisfies the liquid water requirement, as well as a number of these other properties, magnetosphere, active core activity that provides a number of other benefits required for development and sustainment of life. And more than that, the laws of physics and chemistry are really the same everywhere in the universe. So this is a ripe opportunity to think about how life is more common than maybe we think. And so let's talk about the requirements from a molecular level. So life intrinsically requires the buildup from a very simple set of elements to more complex molecules. And so let's walk through that one by one. In fact, some of the most common elements in our universe are shown here: carbon, hydrogen, oxygen, and nitrogen. And these are three key elements that we want to think about how they are coming together in a certain way to build up that complexity. And in that opportunity, there are some common molecules that I'm sure, are familiar with. Methane, I think we all make some from time to time. Ammonia, NH3, that's like your window glass cleaner. Water, H2O, we need, a good several 8 ounces every day, or more than that, I should say. Carbon monoxide and carbon dioxide, which we release every time we exhale. And so these different but very simple molecules must come together in a particular way to start building up what's required for life. And when I say complexity here, I mean building up chains, lengthening the chain architecture, and those chains enable more complicated patterns, different bonding structures. So let's bring up a visual aid here. We're actually talking about the buildup from simple molecules to so-called nucleobases, and really this notion of RNA ribonucleic acid as really the fundamental piece for biology, which then leads to DNA, deoxyribose nucleic acid. That is the key piece here. So how do we go from something that's very simple, these simple molecules, to building up the nucleobases? These amino acids are important and serve as the key molecular building blocks. So one could ask, how does this complexity evolve? What's required to get that? And it turns out minerals, the very minerals that we think of around us, the rocks and components of our daily life, may serve as a key piece. In fact, the surface of minerals may be exactly what's required for building biomolecular self-assembly. So you start with a mineral, and you can think of a mineral in different ways, but here I'm breaking it down to think about how the atoms are actually packed together in a periodic array. And at the surface of that mineral, a monolayer of some very simple, maybe nucleic acid or even simpler, even these molecular species can attach themselves essentially. And the character of the surface layer of that mineral encourages buildup of complexity. It's essentially providing a map. It's providing a key onto which the lengthening and sort of variety of bonding character can take place. And this might be a key piece in going from prebiotic to biotic. So this is another piece that we want to consider in this study. So what are the sort of essential hypotheses that have been discussed so far in the scientific community for origin of life? You might be familiar with this one, so-called the Miller-Urey Experiments in the early 1950s, 1953. Miller and Urey came together and essentially took some of these very simple molecules that I talked about before, methane, ammonia, hydrogen, water, CO2, and they subjected it to an electric spark. Think of it as a lightning bolt hitting a pond, right? This provided the appropriate energy to take these building blocks, these very simple molecules, break them apart, and then reform in a particular environment. And they did, in fact, find that some of these nucleobases, in fact, there are around 70 that are that were discovered in this particular experiment, but only 20 of which, so there's 70 nucleobases that are possible or that we've discovered, but only 20 of those lead to biology. But the question is, why is that? What is it about the nature of those particular nucleobases that lead to biology? So here in this experiment, they did find that that buildup of complexity was possible. Another hypothesis is something called this extremophile origin of life, wherein materials, simple molecules, again, where the input is could be geothermal, enables this extension, this polymerization of more complex molecules. So here is a schematic of something called a black smoker. So when ocean crust is pulled apart, you have magmatic, hot magmatic material upwelling right at that ridge. And you can actually have an interaction, a very complex interaction between the upwelling of this hot magmatic material. It releases gases, a wide variety of high Z, iron, titanium, sulfur, the very rich chemical environment, and it interacts, percolates with the salt water. And it turns out this is a ripe environment and stimulates really not just survival of microbiology of different kinds of organisms, but they really thrive in this environment. You may be also familiar with hot springs or different pools where there's a very extreme pH, could be very acidic, could be very basic. Even in California here, the Iron Mountain region, Shasta County, from old mining work, I think there's quite a bit of microbiology that's very rich. So this notion of extremophile and being able to trace the mitochondrial RNA all the way back to a central piece that shows we all have that in common in the tree of life. That's a really exciting and great push toward this extremophile origin of life. But here we're going to talk about today yet a third option, and that is impact synthesis. So in space, in our solar system and beyond, materials are constantly colliding with one another. And this could be collisions between something as small as a dust grain, meteorites, we're going to focus on that in particular, but even asteroids, planetesimals, protoplanets, and planets themselves. They can collide, and in that moment of collision, that very short time slice, tremendous amounts of energy are given the opportunity to interact and provide that that input that could kickstart life. So we're going to talk about the details of how that actually happens, and our focus will be on on meteorites, wherein these very simple materials, these very simple molecules are basically getting a free ride. But then the process of an impact, of a collision and movement of a shock wave through the material could be this necessary piece to kickstart the complexity. So let's talk about meteorites for just a moment. In fact, there's a wide diversity of meteorites. And here I show a graphic that walks us through several different types, from chondritic material. So they have these very small chondrules, very carbon rich chondritic material. Iron meteorites, you might be familiar with. The Gibeon meteorite is available in certain fragments on eBay. But if you slice into these iron meteorites, the iron and nickel have actually exolved from one another. And they have this beautiful Widmanstätten pattern where you see these lamellae. Also palisite meteorites. This is sort of probably a remnant mantle material from another larger impact, wherein you've got this iron nickel matrix next to olivine or silicate rich minerals that tell you it was once right at that sweet spot for a mantle predecessor. And then you have achondritic stony meteorites, so a wide variety of chemistry. And in fact, I mentioned these 70 nucleobases that were identified in these Miller-Urey experiments. All of these nucleobases have been found in meteorites. And so you could almost think of meteorites as like the solar system Uber. We are moving material around from place to place, and these materials bump into each other, collide, and in that moment of very high energy density states provides the necessary energy to build up complexity. It does contain organic material, and this is another exciting piece to consider. So a little bit more about meteorites. We know that we need to bridge this gap. We need to go from very simple materials and build up the complexity of amino acids. But in fact, many of these amino acids are already found on the meteorites themselves. And we know that we can then consider their origin. We can look at different diagnostics to suss out the origin of those meteorites, whether it was more interstellar medium, protosolar nebula, and even identify the parent body by looking at different kinds of spectroscopy or looking at the materials involved. So we're running down the list of what's required to kickstart the origin of life. So we've got the appropriate chemistry. We have the opportunity for building up this complexity through the collision process. But then I want to point out this mineralogy aspect. This wide diversity in mineralogy actually can benefit, can promote the appropriate templating, the appropriate map onto which these very simple molecules can build up complexity. So previous work in this area, actually not too long ago, 2016, 2015 timeframe, colleagues considered starting with a particular simple molecule, something called formamide. And formamide is a compound, hydrogen, oxygen, and nitrogen. And this formamide, it's actually an ideal precursor material for nucleobases. They've done theoretical studies, molecular dynamic studies that show this is actually quite ideal material to begin with for building up the appropriate nucleobase suite. Moreover, it's abundant. Interstellar media, certainly also in our own, in comets, they've been able to document an abundance of formamide in comet tails and material there. So it's an ideal starting material. And the notion is that could we then take this and through some dynamic process, break it down into its building block radical species, and then have an opportunity, provide the system with the appropriate construction to then build up complexity that looks like these biotic or abiotic nucleobases. And so Ferris et al., they thought this is a great idea, and they tried to do this with a high power laser. And so what they did is they took this formamide and they subjected it to a laser system that essentially broke down all of those simpler species from the formamide. And then they used a set of tools to look at what is the possible buildup of complexity. But the issue, whoops, let me go back one. The issue here is that the time scale over which they looked at this buildup of complexity under a dynamic, high energy density process might not have been quite right. They might be missing certain aspects of that sequence to really identify appropriately the mechanism. That's the key piece. How do you go from simple to complex? And so we are endeavoring on that very approach ourselves in the laboratory here. So first I want to introduce, how do we make these extreme conditions? How do we mimic the collision, the impact event between two different bodies? And so here I show a graphic that sort of illustrates generating extreme conditions in the laboratory. You might think of a hammer. We probably all have one, and that generates high pressure, but just for a moment, by virtue of a force applied over a small area. This is almost equivalent to the kinds of pressure you might have in a can of soda, where you're encapsulating the CO2 gas, and it's kept at a slight pressure inside the can. And when you open it, you're able to hear that release of the gas that's been under some pressure. Certainly balloons, helium that we use in balloons for birthday parties, that's contained in a vessel in a cylinder for high pressure. We move up, and there are different kinds of tools we use in the laboratory. Small pressure devices, ton presses we use, something called a diamond anvil cell, where we actually take two gem quality diamonds that oppose each other, and we generate tremendous pressure, but over a very, very small volume of material. Lasers are another tool that are at our disposal here in the Bay Area. We are fortunate to have the National Ignition Facility over at Lawrence Livermore National Lab, where 192 lasers are all pointed at the tip of a pen, the size, a sample just the size of the tip of a pen. And they're able to create extraordinary extreme conditions. In fact, they're able to mimic the conditions at the center of a star, generating just extraordinary high pressures and temperatures. And here's sort of the counterpart environment that you might think of for some of these pressure simulations or laboratory settings, from the bottom of the ocean floor to a thermonuclear explosion. Certainly the center of the Earth is at tremendous pressure, 300 million times the pressure of our atmosphere here, the center of Jupiter, all the way up to the center of the star. So we have these fantastic tools that help us simulate these same conditions. And here for this talk, we're going to focus on sort of this central region, going from pressures of the bottom of the ocean floor to the center of the Earth. And we're going to do that in a dynamic way, in a time-resolved way. And so when we talk about time-resolved or a rapid application of pressure, we actually think about something that's called a shock wave. So a shock wave is actually a mechanical discontinuity. It is the motion of a supersonic wave in a material. And you could think of a shock wave in sort of this cartoon image, wherein, say, you've got a train moving along, no issues at hand. It's just steadily moving through. But suddenly, some of the cars in the train here, they stop, okay? And there's a response behind those suddenly halted cars. And you have this buildup, you have this sequence of events that happens behind that initial front that rapidly compresses the train cars together. And in fact, you have this sequence, and even at the end, you get the end train cars that sort of bump and then have extension back out. So this is a discontinuity in the material, generates a very high pressure, high temperature state almost instantaneously. And this sort of tool, generating shock waves in materials, is exactly what the asteroids and comets and collisions of these materials, that's what they experience in that very short time scale. But now we want to look at that whole process and visualize what's going on to the minerals, what's going on to the chemistry, to start to disentangle how we build up this needed complexity for origin of life. So you need a really good camera is what it comes down to. You have to visualize step by step the sequence of events at the atomic level. So here's an analogy. At Stanford, a bet was made between two individuals about how does a horse gallop. When a horse gallops, do all of the hooves come off the ground? And if you only have the beginning and the end view of a horse galloping, you don't have enough information to answer that question. You need a sequence of views of the horse galloping in order to discern the mechanism of the gallop, right? So here's essentially, say you only have the beginning and the end. That's not going to be enough. So you have to come up with a technique, a way to visualize what's going on in between. And that's exactly what they did. They set up a series of tripwires. So then they could find out, I suppose it was the second tripwire in, that would then execute shutters on this camera. And they found that, in fact, all the hooves come off the ground. And the guy had to pay his buddy for calling it right on the bet. But this is the same approach that we want to take with our data set, with our testing of this hypothesis. We need a high resolution, ultra fast camera to visualize this process of the breakdown and buildup of chemical complexity during a shock wave. And so to do that, we're going to use a camera here in the Bay Area, so-called the LINAC Coherent Light Source. And this is one of our facilities at the SLAC National Lab, so-called the LCLS. And think of it, you can think of it effectively as a 2-mile long, very long, large atomic scale camera that uses a particular type of X-ray, X-rays with a certain characteristic, I should say, to take images of our samples in the ultra fast, right? So it has a really fast shutter speed. And so here's a view of our linear accelerator. It extends many kilometers long. We've got a LINAC, and then the undulators, a series of magnets, essentially. They oscillate the beam in such a way that X-rays are generated with laser-like properties. And I want to introduce a few timescale notes here. Something called a nanosecond. So 10 to 100 nanoseconds, you could think of, that's about how quickly your processor is working on the computer over which you're viewing this talk. So a femtosecond is 1,000,000 times faster than that. In fact, it is the amount of time that light takes to travel the width of a hair. So we've got two different time scales. We have nanoseconds. This is the time scale over which shock waves can modify a material, can cause chemicals to break apart and reform. So we need a shutter speed, we need a camera that's much, much faster than that time scale. So we're going to take advantage of this femtosecond shutter speed of the LCLS. So I mentioned that the LINAC Coherent Light Source is a very novel X-ray source, an X-ray free electron laser. And there are only just recently now a few of these in operation across the globe. But the LCLS was the first one to operate in the so-called hard X-ray regime that allows us to see through materials effectively. And it has a very short pulse width, right? That's that shutter speed that we need. It's brilliant, so it's 1 billion times brighter than many of our other facilities that experimentalists use. And it's coherent, which means the phase of the X-rays are all in sync. There's not, we're going to take advantage of something called the coherence of the X-rays. And that's something that's afforded to us by virtue of this long undulator series, these magnets that force the accelerator, the electrons to move back and forth rapidly. So we're going to combine that with the opportunity to generate these extraordinary conditions, these very high pressure temperature conditions. So I use an instrument at the LCLS called the Matter in Extreme Conditions instrument, because we're not very creative with our titles here. So the MEC is an instrument that I use. I've used it now for a little over a decade. And it's an experimental facility where we can generate these shock waves and combine it with this appropriate camera. There are a number of other kinds of studies that MEC scientists and colleagues investigate. And this ranges from warm dense matter, the interior of planets, even fusion energy, novel ways of generating clean energy for society. So all of these exciting scientific opportunities are here and available to us using this unique platform. So when I say generate a shock wave in a material, what exactly am I talking about? So here's sort of a schematic view of how this process actually works to launch a shock and then probe what's going on with the X-rays. So here in this view, I've got a sample, let's say a piece of meteorite sitting in the middle. And I bring in these high power lasers. And these lasers are just a tool, another way of generating high pressure. But how does that actually work? Well, I take advantage of Newton's third law, which means for every action, there's an equal and opposite reaction. So I bring in these lasers. In fact, you could think of, for those movie buffs out there, Back to the Future, and Doc says, we need a bolt of lightning, 1.21 gigawatts, right? So we're essentially sending in that much energy onto our sample. We're sending in a bolt of lightning's worth amount of energy using these high power lasers. And we generate a plasma, okay? We start to ablate the surface of our sample. So here come they're so-called drive lasers. These high energy lasers come in and they start to ablate. And what happens is that material turns into a plasma and starts to blow off. So here, these little yellow dots are showing how they blow off. And it's like a rocket effect. As the material blows off in the opposite direction, I launch a shockwave and I generate this very dense, high pressure state, but only for moments, only for nanoseconds, right? And just at this right moment, at the highest pressure state, I probe with the X-rays. So here come the X-rays. Here's this red line coming in. So I've generated my shock. I bring in the X-rays, and now I use a suite of diagnostics. I use something called X-ray diffraction, X-ray spectroscopy, and X-ray imaging. These three different categories of diagnostics to visualize, to watch how my sample is changing in real time. And then we come up with some model. This is work from a colleague of mine to actually see in 3D and work through how does this apply to our scientific question. So I've mentioned these three kinds of diagnostics. These are my eyeballs, basically. This is how I visualize what's going on. I'm going to use X-ray imaging to watch how that shock wave moves through my meteorite sample that's been doped with this fantastic formamide precursor material. I'm going to use something called X-ray spectroscopy that will give me information about the chemistry. How are the bonds actually breaking and reforming in real time? And then I'm going to use X-ray diffraction that basically allows me to fingerprint, to look at how the minerals are changing on that time scale. So first of all, how do we see a shock wave? Well, X-ray imaging in this context is actually very similar to how we image other things with X-rays. For instance, if you go to your primary care physician, you've got a broken bone, maybe you take an X-ray, look at a radiograph or an image of your bones to identify the issue. So we're going to use that same idea, pass X-rays through our sample at just the right time to visualize where is the shock wave. And we've done this in some test samples at LCLS. And so here's some preliminary data. And I show a material, and I've placed in that material synthetically, I've placed a void. I've placed an absence of material, which for the next experiment that I do, I'll actually load this void with the formamide, with the solution, the material that I think is a good opportunity for witnessing how this biotic chemistry changes during a shock wave. So in this image, though, it's just a void, absence of material, and I launch a shock wave in this view from top to bottom. And I take my X-ray shutter, I take my views in a few nanosecond time slices, so 2, 4, 8 nanosecond time slices. And I can actually watch these different ways of the absorption, X-ray absorption is manifested in this way. I can track the front of that shock wave, right? So right where the train cars have butted up against one another, right at that interface, I can track that with incredible fidelity using these techniques. And so here we've demonstrated this visualization in real time. So we're going to do that with an experiment coming up in October to do exactly this with the appropriate meteoritic and formamide components. We will then use X-ray spectroscopy to look at how the chemistry is changing of that formamide in the context, in the host rock or the host meteoritic material in real time. So I send in a different kind of X-rays this time, so-called soft X-rays, to probe the breakdown and buildup in different time slices of these of this chemical, essentially, of this formamide. And so that gives us a visualization of that perspective. And in fact, the LCLS is expecting an exciting upgrade to come online in early 2022. And we're going to use something called a superconducting LINAC. So far, our linear accelerator, the cavities are made of copper, but now we're going to niobium, which is a superconducting material. Has to be kept at cryo. We've got a number of cryo modules that keep it at very low temperature. And we're going to go from 120 pulses to 1,000,000 pulses per second. So my ability to take those appropriately short time slices to visualize this process is at hand. We can do this. And that's one of the most exciting opportunities here, that we have the tools that we need. So an experiment may look like the following, where we've got our meteorite, we've got our formamide, we send in the shock wave using a different kind of laser here in this schematic, and then we probe with these very short X-rays. And we look for changes effectively in the color of the X-ray. So we send in a certain wavelength, and using the soft X-rays, we're going to look for a modification in the color of those X-rays. And from that, we deduce the chemical change. Diffraction, I'm going to move a little faster here. I see we're running short on time, but diffraction, X-ray diffraction of the minerals of that host rock around the formamide is also important, in part because of this notion of templating. And so here, we're looking at that periodic array of atoms packed together in a certain structure. And it turns out for every single mineral, they have a different structure. So you could think of X-ray diffraction as like a fingerprint, and every mineral has a unique fingerprint. So I'm going to look for changes in that fingerprint, in that diffraction pattern, as a function of time. And in fact, I've done some of this work already looking at silicates and SiO2, something is probably a component of the computer front screen that you're looking at. Silica is on the front of your phone. It's really ubiquitous in our daily lives. And it turns out that silicates are, and quartz and feldspar, turns out, are the most abundant materials in our Earth's crust. And so understanding how silicates change under shock compression is very important. And we've done some of these preliminary experiments. And so I just want to share with you the approach here. We, again, take our sample, we shine these high power optical lasers on it to generate a shock wave, and then we probe, in this case with this pink LCLS beam. And we're going to look for this fingerprint. We're going to look for the diffraction to actually change. And I want to share with you the inside of the MEC chamber. This is where the experiments actually take place. The targets sit here in the center. We've got these huge 4-inch optics that actually focus this high power laser onto our sample. And then we've got some cameras downstream that collect that X-ray diffraction, that fingerprint, if you will. Here's actually the hutch where I work. I was just there the other day as an experimentalist participating in beam time. And it's about the size of a person. It's actually quite a bit taller. I can actually go inside. Here's a blue stick person for scale. And I can actually crawl inside, and I do, to position the different diagnostics that I require. Here's that sample in the center. This is about 2 meters wide. So I can get in there and crawl around and move different optics as I need. So here's an example of an X-ray diffraction pattern that I can resolve in real time. Let's say I initially start with glass, SiO2 glass. And it turns out that for disordered or amorphous material, I actually don't expect to see any of these specific lines, specific locations of intensity that tell me what the structure is because it's intrinsically disordered. But when I send my shock wave through and I probe with the X-rays at just the right moment, I get a beautiful change. I get this really gorgeous diffraction pattern and these locations of intensity of new peaks tell me what this material is. And it turns out I'm breaking the bonds in a glass and I'm reforming the oxygen and silicon in a brand new way. So this is witnessing something called a reconstructive phase transition. This is really exciting. And it's the same sort of approach that we want to use for our origin of life studies. So we're going to combine all of these techniques in a few different experiments at the LCLS to pull apart the different components, watching the shock wave, watching the change in chemistry, and thinking about the templating of the appropriate minerals and how they change. And I actually want to end, or almost at the end here, on a note that this is so relevant right now, these sorts of studies. And as we think about possible, or the Mars sample return mission underway with Perseverance, as we think about other bodies in our solar system, let's take Enceladus, the moon of Jupiter, that has this beautiful so-called chaos features, these linear features that show us where the ice is actually breaking apart and the liquid water below is active and is dynamic. And these are all the appropriate ingredients required for life. And so I think we're actually in this, we're right at the precipice. We're about to take an exciting leap, I think, forward in thinking about the origin of life. And I fully believe that we're in a position to understand that it's actually far more common than we previously thought. And I certainly want to thank all of the collaborators and researchers that I've worked with over the years. These experiments are incredibly complicated and require very large teams of people. And the folks I highlight here in bold are actually participants on the upcoming experiments we'll have in October that actually look at the breakdown and buildup of complicated chemistry, pursuing questions around the origin of life. And I'll leave you with a quote. The history of humankind is hung on a timeline of discoveries. And I think this is what's next. Thank you so much. And I'm happy to take questions.
Well, thank you for that. An interesting talk. I'll start off with a question of my own. I was really surprised to hear how you're doing 3 experiments at once, essentially, with the beam, and I thought astrophotography was complicated, but the calibration time has to be immense. I'm just curious. I mean, of the amount of time for experimentation, how much time is required to calibrate these instruments so they're detecting your experimental event at the exact same moment?
That's a great question. We do spend quite a bit of time, many hours. So oftentimes these different end stations of LCLS and really of any light source. So LCLS and X-ray free electron laser, what's here, is just one of many Department of Energy light source facilities. We also have SSRL, so the Stanford Synchrotron Radiation Light Source. There's also one in Berkeley. There's the Advanced Light Source, a partner with Berkeley, or a part of Berkeley National Lab. And these light sources, they each have different end stations. And so instrumental or experimentalists such as myself can go, we apply for time. And often there's a lot of work done by the beamline scientists up front, many days, many weeks, many months even of commissioning to do exactly what you're talking about, to calibrate detectors, to calibrate sensors, to optimize timing and synchronization of all of these different pieces so that when the scientist arrives, effectively, we can plug in and execute our scientific scope with incredible precision and efficiency. Now, of course, you know, stuff happens, things break, cameras don't work. There are times when you're troubleshooting for many hours. I will say with the LCLS, what's fantastic is it's this phenomenal X-ray source that has these laser-like properties, and it can tune up within a few hours. So we can come in as an experimental team, and 2 hours into our shift, we're off and running. And different facilities have different sort of shift run times. So I'll go in for a 12-hour shift, and then repeat that. So we're like 9 a.m. to 9 p.m. That's sort of our operational for 5 days in a row, let's say. That's sort of our approach.
And another question I have is, you know, we all know that we have found traces of amino acids in molecular clouds when doing spectroscopic studies of distant parts of the universe. Are you trying to reproduce that process or some percentage of that process? Are you expecting to actually see these precursors as a result of this experiment, or is it some subset of you know, something on the pathway to amino acids, or you don't know yet?
You know, I think when I first started this project, I was hoping for the smoking gun, right? I was hoping to see, oh my goodness, it's an RNA chain. But actually, I'm truth be told, I'm not a biologist, right? I'm a mineral physicist, I'm a shock physicist, and so it is a sequence of steady steps, right, in our approach to document what the chemical complexity, so-called the kinetics of the chemistry. And I think it will be, what will be revealed is that it is a stepwise process. So we are first going to look for precursors, then we're going to introduce these appropriate templating minerals to see how do those precursors actually develop in real time additional complexity that is toward the nucleobase sequence. And then even further than that, at much longer time scales, move toward, you know, an RNA structure. So there really is a stepwise process in our approach. I think we need that. I was naively many years ago hoping to just see, you know, oh, there's the creature from the shock compression. But no, it is a buildup of the chemistry that we have to monitor incrementally. Yeah.
Okay, that makes a lot of sense.
Yeah.
Let me see. Do any of our participants out there have some questions? If so, oh yeah, go ahead, Dave. I just want to remind people that if they do have a question, please type it into either the chat or the Q&A window, and we'll relay it to Arianna.
Ari, I have a question about the composition of the substrate that's holding the formamide. Are you trying different types of substrates? Are you trying to simulate different types of meteorite compositions in those substrates?
It's a fantastic question, and the answer is yes, absolutely. So we're going to start with something that's very a simple rock matrix, and it will actually be synthetic. So we're starting with quartz, effectively SiO2, a matrix, and we're going to use a method that was actually also deployed for doing some of the sample recon for Mars rovers, where we have very calibrated host rock material because we don't want any contamination. So we're going to start very simple, and then we will we will dope with certain amounts of iron nickel, certain amounts of titanium oxide, so-called anatase, and we will have this approach of sort of methodically moving through different chemistries that theory and modeling has shown to promote the complexity buildup. So the answer is absolutely yes. And I think there have been other studies sort of on the other end. So we're focusing on the in situ breakdown and buildup of the chemistry. There've also been a lot of cool studies on shock recovery. So this is after the fact. So you have an impact event, you have a meteorite or a material coming in, and what does that do on the surface of a planet? Maybe that planet already has water. And so actually looking at clays, looking at different layered silicate structures. Maybe you're familiar with talc or montmorillonite that's often used in cement production. But these different clay minerals are also very attractive because of their layered structure and can provide that appropriate template.
Fascinating.
Andy asked a good question. Is there a website where we can follow your progress?
Oh, that is a fantastic idea. I will put that together. So
That'd be great.
I should say, as part of my my work portfolio at Slack, we do have a high energy density group at Slack. Also, as a part of Stanford campus, we have the Extreme Environments Laboratory. So either of those sort of sets of keywords and my my efforts will pop up. But specific to this project, I don't. And I think as we make more execute more experiments, I would be delighted to do that. So
yeah, please send us
a great idea.
Yeah, please send us a link when that happens.
Sure.
No pressure or anything here.
No,
but
no.
but,
come October,
yeah,
come October, it'll be hot off the press data.
All right, that would be great. We'd love to follow the progress on this. It's really an interesting experiment.
Yeah.
Let's see if anybody else here has any questions. Anyone else? No. Let's see. I'll check Facebook. Nope. Well, I don't see any other questions.
I have another question or two.
Please.
If you don't mind.
No,
Sure.
I don't mind.
Arianna, whenever I get an X-ray, I always ask my X-ray radiologist, what is the wavelength of X-rays that you're doing? And they usually don't know. And I happen to know that the typical X-ray runs, if I remember correctly, it's 1 angstrom. Am I right on that? And
yes.
What are the wavelengths of the high energy X-rays that you're using roughly? What's the range?
Yeah, exactly. So a fraction of an angstrom for sure, down to 0.2. So, very small fractions of an angstrom. So just to give some perspective, the utility of the X-ray wavelength is that they're just the right length, they're just the right size so that they interact with the atomic lattice. So it's the spacing between the atoms. There's a whole suite of different wavelengths on the electromagnetic spectrum, all the way up to radio waves, right, which just pass right through our body. But X-rays are just the right wavelength so that they can provide this definition for us, this visualization of the structure. And so you're exactly right. Angstroms is right on the mark.
Okay. Can I ask another question, please? Sort of, maybe.
Sure.
Rich, I don't want to run you too.
No, it's not a problem, Dave.
Okay,
we have plenty of time tonight.
Okay. How much energy is there in the shocking laser, roughly?
So we are operating at 100 joules of laser energy deposited over something called a spot size. So the footprint of the laser is only a few hundred microns. So to think of this in a different way, we're taking all of that energy and putting it in sort of the width of a hair.
Okay.
So it's very small. So 10 to the 13 watts per square centimeter.
Wow.
So yeah, this is very high intensity laser system. But I should say there's a big spectrum of different kinds of lasers. And so my job is to sustain that shock wave over the appropriate time scale to watch the chemistry take place. So nanosecond time scale. There are other lasers available, so-called short pulse lasers, which happen on much shorter, few picosecond time scales. And there, the watts per square centimeter, oh goodness, 10 to the 19. So many orders of magnitude. So there's a wide range.
Okay. Thank you very much.
Okay. All right. Well, I don't see any other questions. So unless you or I, Dave, can come up with some real quick, I think, yeah, go for it, please.
I actually have several, but I'm trying to restrain myself.
No need. How often do I say that?
Not very often. Ari, I want to tell you the reason they made me program director was that I asked more than 50% of the questions. So
Okay.
I was interested in the superconducting aspect with the niobium. What is the temperature you have to get the niobium down to? I assume it's within a degree of absolute.
Yeah, that's a fantastic question. Our cryo modules are certainly operating in the maybe tens of Kelvin, something like that. It's much colder than the traditional liquid nitrogen sorts of temperatures. So these are many different cryo modules that actually have to cool down the entire structure. So yeah, it would be,
That's going to be really exciting when you can get that type of timer. I mean, that's just incredible. Wow.
Yeah, this is one of the reasons why I was so excited, motivated to pursue this with our number of fantastic colleagues, because we're at that point on the technology, right? So our X-ray technology, our drive laser technology has brought us to this moment where we have the appropriate resolution. These other studies that have been done, very pioneering studies, but what happens in that first few nanoseconds, what happens in the first tens of picoseconds could tell us critical information about the mechanism of this dynamic chemistry and the infrastructure, right? How that chemistry, where that chemistry is taking place, that we've never been able to witness before.
Yeah.
And so these are the kinds of novel experiments that really open our eyes into the fundamental physics and chemistry properties that dictate a number of things. Origin of life is this example, but in fact, void collapse or pore collapse and the chemistry that follows could be another aspect in important work on explosives, right? So think of our munitions, right? The US munitions or different infrastructure there. It's the chemistry that takes place in those energetic materials that is really the key to understanding how they work. And it's really now with these X-ray free electron lasers that we have the right camera. We can visualize this. Yeah.
A couple of questions. Frank asks, have there been discussions about what might happen with big impacts on Titan, where the target might include water ice, liquid methane, and ethane, and complex organics formed in the atmosphere with at least a little nitrogen from the atmosphere? I mean, are you considering these other aspects of collision chemistry, I guess, in your theories and in your approach?
You know what? Absolutely at a high level, but we're trying to approach this in a sort of simple fashion at first to understand how the different components are behaving under dynamic compression. I will say we've done studies and colleagues of mine have done studies on shocked water, ice, shocked methane, these different, so take each of those one by one. And those studies have been looked at just from, say, the diffraction perspective. But now we want to bring in the soft X-ray probes to look at the chemistry. I will say that is a ripe opportunity for research. So that hasn't been done, in part because we didn't have the technology, we didn't have the X-rays, we didn't have the tools to do this until now. So I will say, yes, absolutely, that's a direction we want to go. At this point, no, we haven't orchestrated that yet.
Danny asks, I know you're not a biologist, are nucleobases definitely the basis of life? And how do we know what parts of life came first?
That's a great question. I will say my sort of cursory knowledge in this is that the amino acids are effectively built up of these different components of the nucleobases. And all life as we know it have in common 20. So there are 20 nucleobases out of the 70 that can form. There are 20 that tend toward life. And why those 20? So there's a hot discussion in the research community around chirality. So if you recall images of the DNA, the double helix, right? Or RNA, these different helical bands, you can have right-handed or left-handed. And it turns out that all of the there's a similarity in this called homochirality in what is a biologic predecessor. So why that chirality? There's actually like a 50-50 chance when these nucleobases form and build up that they could go either way, right or left.
Right.
But for some reason, which is still active area, very active area of research, life prefers, I believe it's right-handed. Yeah.
That's very interesting. So you might discover that just as a result of, from your collision experiment, if you end up with a large percentage in the same chirality as DNA and RNA here on Earth, and there's something very fundamental, maybe in terms of the universe, in producing right-handed chirality. That's very interesting.
Yeah. It would be exciting to see. So I think that's one of these questions that we want to try to discern. And then looking at the other hypotheses, right? So the Urey-Miller or Miller-Urey and extremophile, right? There's actually so much work in both of those categories that has been done, and understanding how the chirality is tracked through those different sequences is also exciting too.
If I remember, the Murchison meteorite had exactly the opposite chirality that we have on Earth.
Oh, really?
Right.
Yeah.
That's exactly right.
Oh.
Yeah. So it had all the nucleobases, but the biotic, the genesis of biology chirality was actually not present. Yeah.
So it was localized. So that means it was some initial conditions here on Earth that led to the preponderance of that chirality, probably. Anyway, that's getting into the weeds here.
Yeah, well, and I'm not an expert. I want to, my caveat is that any biology information is subject to just do a quick check.
Yeah, for sure.
Yeah.
Sam asks, how are we able to know where collision deposits come from if we don't have samples from other places to compare it to? For example, saying Mars collisions may have contributed to life on Earth.
That's a great question, and there are different aspects of the mineralogy, in particular looking at isotopes and how isotopes fractionate. You can trace parent body locality using these isotopes, and I'm not an isotope geochemist per se, but I know that that's certainly a strategy that's used, and is another way of fingerprinting actually localities of different materials. And so you can use remote sensing as well to look at or sample return maybe from the moon or Mars or other places, if you have that luxury, and then you can compare to the isotopes we have in the meteorites. And I think that's a large way in which experts in meteoritics who study this very diverse portfolio of meteorites actually do categorize those materials.
Great. And we'll close with one last question from Andy. What result would you consider to be a historical success?
Oh, goodness. Yeah, I think being able to witness the formamide radicalizing, basically breaking down in the few first, tens of picoseconds, and then forming something more complex. And when I say something more complex, I don't know. There's a number of theories I could pull out and say, oh, it should be this, it should be that. But I think that in conjunction with mapping how the mineralogy is changing, like a one-to-one, I think those two pieces of information will be very profound. I don't think I'm going to see like a little creature waving back at me. That would be really cool. But I think in reality, we'll have to walk through the data and watch for that complexity and really a synergy between the chemistry and the mineral physics. I think that's where the good stuff is.
Yeah. All right. Well, thank you so much.
Well, thank you guys for
brilliant
the
stuff. Yeah.
Yeah, really appreciate it.
All right. Take
Wonderful.
care, everyone.
We'll see you next time. Take good care.
Thank you all for joining us.
Okay. Bye-bye.
Bye now.